What we're going to do now is try to combine some of the radar estimations with near storm environment, which can give you an even better signal. So a lot of this isn't just simply look at the radar and that's all you have to do. Let's wrap the environmental information in there and see if we can help improve our damage rating estimates. So again, we're going to kind of summarize the tornado detection with the 88D, focusing on significant tornadoes because these are the ones we're most interested in. Again, you need to make sure that we've combined the radar attributes for the same time and place. Everything's consistent. Don't look for just one thing. Look for all four elements if possible. And the most important ones would be the velocity with the reflectivity. That's the key because if you have high reflectivity, that means it's dominating the return signal, not something else. So here we've got the storm relative velocity. Generally, once you get above about 40 knot rotational velocity, you tend to get stronger, deeper circulations. You get higher probabilities of EF2 or greater tornadoes when the correlation coefficient drops below about 0.8. Again, most of the default enhancement curves on GR2 are designed to highlight that. It shows up really obviously when the correlation coefficient drops below about 0.9. So anything, you get any depression in the correlation coefficient, these color curves are designed to highlight that. And again, more obvious and deeper lofted debris signatures, stronger tornadoes, but you want them with relatively high reflectivity. So everybody, you hear people throw around the debris ball all the time. It means nothing without the velocity couplet and the CC reduction. You can almost say that there's no way it can be occurring unless you have both of those with it. So trying to make that call from reflectivity alone, just look at the other base radar information, and then in some cases you'll even see low differential reflectivity, but that one doesn't always show up. Okay, you do have to consider the storm environment and what are your expectations to begin with? If we've got STP of 0, what do you do with a 100 knot rotational velocity signature? And it's not just a 0 because the mesoanalysis broke and the whole thing's wrong. You think that's really what the environment looks like. So the point here is what you expect based on the storm environment plays a role in this. So back to our, I think this is just a little later, Louisville, Mississippi. Again, classic. This one, you just step through, everything lines up temporally, vertically, and it's a classic signature. You throw this in, and again, in this case, you would plop this one into you know there's a tornado, so you're going to get estimates of the various EF scale damage ratings. Okay, now what would you do if you throw the storm environment in there? How's that going to help improve the estimate? Let's look at the STP. This is one, now you notice the slope of these plots isn't nearly as steep. The other ones, similar kind of plot, they were much steeper, sharper slope to it. This one's flatter, but as you go to the right, you're getting into higher STP values, and the probability of tornadoes just given a supercell goes up. So once you get around a 4 or 5 STP, there's about a 40% chance that you'll have a tornado in a given grid hour, which is, that's actually pretty high, saying any supercell in that environment, there's about a 40% chance during that hour that you'll get a tornado. That's based solely on the environmental information. And you notice the violent tornadoes, those probabilities never get very high. They're extremely rare no matter what environment you piece together. So here, if we combine these, we can come up with some two-dimensional plots of what's the relative influence here. So probability, VROT increases on the y-axis, or x, sorry, y-axis is STP. So the slope of this shows that most of the influence is the rotational velocity signature, but there is a slope back up to the left. So that's the component of this that the environment's controlling. And so, for example, you see the star there. This is that Alabama case and that we looked at just a little while ago. That one with a rotational velocity around 70. This one would fall in somewhere in the 55 to 60% chance of EF2. The South Dakota case that had the impressive tornado, similar rotational velocity, but it's in a more dangerous storm environment, and it actually has an EF4 rating. Neither one of these places is super high density population, and actually the one you would expect to be underrated would be this one, because it's much more open country. There's a lot more forest and small towns in the Alabama case. So again, this shows for the same rotational velocity, there's an increase of about 15% in the probability of any particular tornado outcome. So in this case, the chance of a significant tornado goes from 55% up to about 70 or 72%. So it's worth considering to have that about 15% improvement. Okay, so real world comparison, let's see how this works when you do it. Let's get some real storms and try to think about the questions. How much, is the tornado damage controlled by the radar signature? Is it the near storm environment? And just think about this as we look at the case. So here's a sounding, near proximity sounding. This is from April 14th of 2012, or 0Z on the 15th. This is Lamont, Oklahoma. Moderate Cape, strong vertical shear, STP 6.7, that's pretty big. Here's the Moore tornado sounding from early afternoon, around midday. Big Cape, at this point, STP is not too high, but there was an increase in low-level shear a little bit later. So we look at the mesoanalysis, STP is instead in the near vicinity of the storm is up as high as 7. And this one in the vicinity is up as high as 12. So these are both upper echelon storm environments showing you near the time and the location that the tornadoes occurred. We'll look at the radar. So this is the Twin Lakes radar. This is not what you want to see if you live in Moore. Certainly, we've got our, and in this case, unfortunately, it probably is the debris ball signature because everything lines up. This is the one on the Kansas-Oklahoma border. Very similar storm structure. So if you look at these, the radar here is just off to the southwest of it, but it's about the same distance. Very similar storm structure. We get a peak rotational velocity on the Kansas-Oklahoma border one in the low 90s or 91.8. Lo and behold, we have the exact same rotational velocity for the Moore tornado. Now it's kind of cheating, you guys, and they're sampled within 100 feet of each other above the ground level or radar level. So this is about as similar as you're going to possibly be able to get. Okay, we've got the tornadic debris signature because that's with the high reflectivity, this little reduction in CC. Same thing with Moore, it's a little broader there. So what happens? So we'll just summarize our environment. We've got all the other stuff. We have large VROT, high probabilities of significant tornadoes. Now, so the question here is, how does the outcome compare to the data? Because this is about as good as you're going to get for analog cases. There's the variation in the EF scale ratings. 4 categories. So you might think, well, how on earth can they be that different? Do you think the tornadoes were that different? Or is there something else that is drastically different between the Kansas-Oklahoma border north of Enid and Moore? It's damage indicators. That's first and foremost. Well, if we look at this statistically, here's a case from southern Alabama or the Florida Panhandle. This is out from the Mobile radar. And we have everything lines up. We've got a rotational velocity 58 knots, a little bit smaller supercell. It's not quite as intense. This one produced EF3 damage. So you're like, wait a minute, these things are all over the place. Damage indicators matter. You have to know what's in the path of the storm. This is a plot here of the just Mississippi, Alabama tornadic storms in the solid lines, and then Kansas, Oklahoma. Sample sizes are real similar. They're both in the order of 400 to 500 tornadoes added together. Notice here, I'll highlight in this one, like you get in the rotational velocity in the 50s, the probability of an EF2 is in the mid to upper teens for the plains right here. Same rotational velocity in the southeast, it's more than double that. And then you just continue up, EF1 plus in blue, you go from low 40% to an EF1 plus is likely. The only difference, these are exact same observing systems, the only difference is there's more stuff in the way in Mississippi, Alabama, consistently. There's trees everywhere, little towns scattered everywhere. There's a higher probability you're going to encounter stuff. So just because you have the signature doesn't mean you're going to get the damage, but does that mean the potential wasn't there? You offset one of these tornadoes in the plains, what tends to happen is you'll have 3 or 4 in open country, and then there's one Greensburg, where it does, unfortunately, encounter the small town. And then it reveals the damage potential because it's got stuff to hit. So again, you want to make sure, do you know if there's a tornado? Do you have high confidence? Are you going to have damage indicators to reveal the intensity of the tornado potentially? And you would be foolish to not consider the near storm environment. if you're going to go through all the trouble of interrogating the radar properly, don't lose sight of the fact, what do you expect in the first place? And how should that temper your expectations overall?